Hello guys, welcome back to NCERT specifics. Today we're going to be discussing alcohol, phenol, and ether. So I'll be reading one paragraph and letting you guys know what is there in this chapter. So yes, guys, they have given structures of functional groups in alcohols. The oxygen, the OH group is attached to carbon by sigma bond. Okay, this and all is fine. We need to know the bond angles, right? OHC bond angle in phenol is 109 degrees. Methanol is 108.9, which is almost 109 degrees, and methoxymethane it is high, which is 107 111.7. Okay. So as you guys can see, the CO bond length is almost the same as in alcohols for what do you say this ether. Okay, ethers you can easily mark. Now preparation of alcohol, I'll just be summarizing. From alkenes you can prepare from acid catalyzed hydrogenation. I mean hydration, and that everybody knows these two mechanisms. It's the easiest mechanism of NCRT. Then you have diborane reaction, like the diborane wala reaction, that is also very common. But just remember, this mechanism that they've given in NCRT is different from what our teacher teaches in the class, but basically they will ask this only. So HBH2 attacks on each of these. Okay, each of these, and then after that you pass through your one more of the alkene, and then you keep passing it and you keep passing it, and you get Br3. Okay, Br3. Then after that you just hydrogenate it in presence of peroxide, and it forms propanol. So first it forms one BH2 with um one of the R's. Let's say this is called R actually, and then this forms BH2R. Then again you do it, it forms BHR2. Then again it forms Br3, and then Br3 in presence of water will give our propanol. Okay, which is ROH basically, right? Okay, so the addition of borane takes the boron atom get attached to the sp2 carbon carrying greater number of hydrogen atoms. It is opposite to Markovnikov rule. In this reaction, alcohol is obtained in excellent yield. Now, reduction of aldehydes and ketones in presence of palladium catalyst or NABH4, LiH4. These are the specifics we can use. Basically, ketone, aldehyde, they all get reduced in terms of H2PD. RC double bond O R dash also gets reduced in terms of SNABH4, which is sodium borohydride, and aluminium hydride, though we know that this is the reduction. And one thing that we tend to miss is LiLH4 is an expensive reagent. It's an expensive reagent. Commercially, acids are reduced to alcohols by converting them to esters, and followed by the reduction using hydrogen in presence of their catalyst, which is catalytic hydrogenation. So first you formation of the ester, then after that you just hydrogenate it. Okay, this is a very specific reaction that they had given, and that is why LiLH4 is not used to prepare the alcohols from other functional groups. Then from Grignard reagents is the normal mechanism that we have been following for a very very long time. Then you have phenol, which is also known as carbolic acid, was first isolated in the early 19th century from coal tar. Okay, coal tar is something that you might have to remember. Okay, so this is the preparation. First, you have this Dow's process. Dow's process, everybody knows, sodium phenoxide wala. It stays as sodium phenoxide until you give H plus, which is kind of obvious. Then you have benzene sulfonic acid, which is sulfonated with oleum and benzene sulfonic acid. It's converted to sodium phenoxide. Okay, so basically what happens is SO3H is a decently good leaving group. So ARSN will happen very fast in the presence of NaOH. So yep, that's all. And then from diazonium salts, like you can prepare it easily because diazonium is a very good leaving group and it releases N2, and you can easily prepare your alcohol. Obviously these diazonium salts are highly unstable in room temperature. And then you have cumene. Okay, this is very important because they've asked the intermediate, they've asked absolutely everything from here. It is converted to phenol and acetone. They've also asked the side product, so make sure you are remembering the side product as well. by treating it with dilute acid. Okay, so first you are treating it with ozone. Ozone forms this intermediate called cumene hydroperoxide, and then after that it forms the um what do you say, the a phenol, right, the carbolic acid, and it is obtained in large quantities. Acetone is also obtained in large quantities, they're saying, so it's a good preparation for acetone also. Then physical properties, many things we have, I'll just narrow it down to two to three things. So as you guys can see that there is not much actually in physical properties. They've just talked about boiling point and sadly nothing about melting point, because that's usually, the one that we cannot do by logic, right? So you have to remember this order: ethanol is greater than ether is greater than propane, because of extent of hydrogen bonding, which is also like, very obvious. So yep. Then solubility in alcohols and phenols in water is due to their ability to form hydrogen bonds. That's all. Okay. Then it solubility decreases with increase in size of aryl and alkyl groups, because they are hydrophobic. They are hydrophobic groups. Okay. So that's all. Then chemical reaction involves um the basic stuff, right? It's very simple. This is when H plus attacks on the OH, forming it a good leaving group, and many things can do this. TS, meaning, what do you say, tosyl chloride. Tosyl chloride can also do this job of converting OH into a good leaving group. So many things we know because of notes and a lot of other external books that we have solved. Now, reactions involving cleavage of OH bond. Okay, basically cleavage of OH bond. Where does it happen? Right. So this is something that we tend to miss, right? So obviously, Na, say alcohol can release H2 from Al. Okay, Al is not mentioned that many places, but we can remember it that Al also causes the oxygen group, the hydrogen in the oxygen to leave. So this hydrogen is leaving and forming H2. Same way, it can also be done for sodium phenoxide, which will be better because the negative charge on the O minus can easily be in resonance. And it also reacts with, what do you say, any base, right? Because slightly acidic to hai by phenol. So yeah, that's it. So yeah, there's one more thing that we usually forget to notice, that alcohols are weaker acids than water. Okay, alcohols are weaker acids than water. So yeah, this reaction shows that water is a better proton donor. Okay, proton donor. So it could act as a bronze state base, which by the way it happens kind of when ROH and in H plus medium when it attacks the lone pair. Right, that is also a possibility, and they're saying that is called a bronze state base, which is true. They have given that aerosols are less acidic than phenol, which is obvious, meaning we can literally put our logic that we have learned for 2 years, दो साल गांड फटा मेहनत कर रहा है भाई. So yes. Then esterification, all right. Esterification is very important, and we tend to miss a very important point in this. So obviously we know the basic mechanisms of esterification. H plus medium में जाएगा और it'll also be reversible. Okay, but this reaction, okay, AROH with COCl forms this what ester, right? This the reaction with carboxylic acid and acid anhydride is carried out in the presence of small amount of concentrated sulfuric acid. Reaction is reversible, and therefore water is removed as soon as it's formed. That's why we use the concentrated sulfuric acid. Okay, and the and acid chloride. Okay, the acid chloride is carried out with the presence of base pyridine. Okay, so as to neutralize the HCl which is formed during the reaction. This can be asked very nicely in JEE mains. It shifts the equilibrium to the right hand side. Introduction of acetyl group in alcohols or phenols is called as acetylation. Acetylation of salicylic acid produces aspirin. Okay, here in whenever note, okay, note it down because they can ask it in very cheeky ways, that pyridine is required. Okay, pyridine is required when Cl is released, when HCl is released, so that the reaction does not go backwards. See, they are saying that primary alcohols do not produce turbidity at room temperature, but there's a chance that SN2 can happen. Think about it. Alright, remember phosphorus trihalides, they produce H3PO3 as the side product. Okay. Dehydration under mild conditions, we all know it is just the basics, right? It's that what we did many, many times. And yeah, we don't need that much heat. And we know the order as well because of common sense. So, yep, I'll be easily skipping all of this except oxidation. That's when the fun starts. So, bro, NCRT basically says that CrO3 anhydrous, okay? Anhydrous CrO3, it produces RCHO, okay? And it's not that good of a reagent. They're saying that, what do you say? PCC, pyridinium chlorochromate, CrO3 in pyridine salt, forming a salt of pyridine with chlorine, okay? It's better for the oxidation of primary alcohols to aldehydes, as you guys can see. Chromic anhydride, CrO3, two names they've given, CrO3 in anhydrous medium and chromic anhydride. So this you have to mug up. Sec alcohol becomes a ketone easily, bhai. So tertiary do not undergo any oxidation reaction, that we know for sure. So this pink part is generally something that we always tend to miss. Under strong reaction conditions such as strong oxidizing agents and elevated temperatures, cleavages of various CC bonds take place, and a mixture of carboxylic acids containing lesser number of carbon atoms are formed. We all know this Cu wala reactions. It's kind of obvious. It's actually very obvious and non-counterintuitive. Very easy reactions that we don't tend to forget usually. Cu 573 Kelvin. How many times you have seen that reaction? Many times you've seen a CH4 to alcohol, right? CH3OH. We have seen this using Cu 573 Kelvin back in the hydrocarbons chapter. Please check it once. Then reaction of phenols, okay? Reaction of phenols. Following reactions are shown by phenols only. So dilute HNO3, dilute HNO. Everyone has confusion in these kind of shit, right? Low temperature yields mixture of ortho and para. Okay, ortho and para ki mixtures. They can be separated by steam distillation. It can also be used to prepare picric acid, but the yield of this reaction is very less. Okay, yield is very bad, bad yield. Then proceeding, we have the what do you say? Picric acid preparation. Preparation by treating with phenol first with concentrated sulfuric acid, which converts it to phenol 2,4 disulfonic acid. I have written these reactions. Remember the first one especially, because first it converts into disulfonide mixture, then it converts it into double triple NO2. Then you have Br2 and CS2, which is for the addition of Br. In non-polar solvent, CHCl3 is also allowed. Mono, and it's considered in low temperature, meaning 0 degrees kind of type shit, right? So it is because of the highly activating effect of OH group that directly the bromine molecule can go. It doesn't need a Lewis acid like AlCl3. So then you have tribromophenol. This is in bromine water. Okay, remember, ये तो bromine water है, water. Okay. Then the next thing that we have to remember is Colby's reaction. Colby's reaction is phenoxide generated by treating phenol with sodium hydroxide is even more reactive to phenol towards um this and all we know, right? Basically, what I want to um outlay in this is, if you add CO2, if you add CO2, it forms salicylic acid. Okay, CO2, first you form the phenoxide ion, then you form CO2, you add CO2, and it forms salicylic acid. Reamer Tiemann reaction, there was 60 times in JEE mains at least. Okay, first, obviously all of these intermediates are very important, so we'll be remembering them. First you have phenol, then dichlorocarbene. Okay, dichlorocarbene comes and attacks your place, which is your intermediate. Then you put NaOH and you will get this. Obviously the mechanism a little more complicated, so you can just refer to your notes for that actually, because this is just the basics that we need for now. So I found something that could be asked. See, chromic acid, okay. Chromic acid produces benzoquinone, that we know. Another reagent for that is MnO2. That is by the math on we have learnt it. And in the presence of air, okay, this is where in the presence of air, phenols are slowly oxidized to dark color mixtures containing quinones. This is how we get trapped in GE, because these stuff, okay, they'll be like, oh, bro, this is out of syllabus. But no, it's all there in NCERT. They're just testing how well do you know it. Phenols are slowly oxidized to dark colored mixtures containing quinones. So the next part is commercially important alcohols. So in your lower grades, you probably learned that destructive distillation of wood gives you wood spirit, which is also called methanol. Now, carbon monoxide with H2 dihydrogen in ZnOCr2O3 573 to 673 Kelvin gives you methanol. This is a very forgotten reaction, remember. Otherwise, we know that obviously it is very it causes blindness. We know methanol blindness. We know all these normal cases. Solvent in paints, varnishes, and chiefly for making formaldehyde. So there's two things that are over here. First, you have conversion of sucrose to glucose and fructose, which is from invertase, and then zymase converts this given glucose or the decomposed sucrose into the respective ethyl alcohol. This is a very important reaction. It has come in a P by Q. Maybe something that we need to know is fermentation takes place in anaerobic conditions, absence of air. Carbon dioxide is released during fermentation of wines. I have no idea whether this is important, but if air gets into fermentation mixture, the oxygen of air oxidizes ethanol to ethanoic acid, which in turn destroys the taste of alcoholic drinks. So they have talked about denaturation of alcohols. Basically, commercial alcohol is made unfit for drinking by mixing copper sulfate to give color and pyridine to give it a foul smelling. And it's also called as denaturation of alcohols. This is pre-boards question, but it can also come in JEE means. A large quantity of ethanol is prepared by hydration of ethene that everybody knows. These two temperature make sure to get it under control 443 Kelvin and 413 Kelvin. And another rhetorical question is given here, which the answer is that basically, when we try to prepare it, okay, with two molecules, it will form a bunch of different ethers that we don't want. That is the reason. Williamson ether synthesis is very basic. It is what we've been learning since day one. And here specifically tertiary butyl, they've given tertiary butyl will undergo your E2, actually E2 reaction, because of the presence of a strong base. Oh, CH3O is always a strong base. CH3O minus, always a strong base. You can convert phenols to ethers, and it's used as a phenoxide moiety. I don't know why they use that, because basically it does SN2 on this RX, even though it's not a good nucleophile. Something that you guys might need to know is that even though this has an oxygen and it has four carbon, still N-pentane has more than ethoxyetane. So the order becomes butanol, then N-pentane, then you have ethoxyetane. This could be asked directly in your JEE mains. The order of reactivity of hydrogen halides is HiHbr HCl. HiHbr at high temperature is caused by cleavage of ethers. They have given a funny name for anisols, this thing, meaning uh, the ion formed, okay? Methyl phenyl oxonium ion. This can come in assertion reasoning. And therefore, the attack, yeah, so everything else is normal according to your normal um, ether, what do you say, the Williamson ether synthesis, right? Then you have electrophilic substitution, something that's very important that we tend to miss. Br2 and ethanoic acid is enough for anisole. Because anisole is a pretty nice activating group. We have two lone pairs on top, and that is helping us activate the ring, right? Activate the ring, increase the electron density in the ring. So we just need ethanoic acid. We don't need iron 3 bromide. Even in the absence of iron 3 bromide, it is activated, right? So that's why. FCA, we know we have, I'm going to skipping it. Anisole with the nitration gives you the only para, okay, in nitrating mixture. And that's where this chapter comes to an end. Please watch this video on 2x if you want most efficiency.